In the spring of 1846, Michael Faraday had penned a paper called Thoughts on Ray Vibrations. In that prophetic publication, he speculated that light is a type of vibration in the lines of force. The lines of force, he wrote, are known to connect particles and also masses of matter together. In other words, in Faraday's imagination, electric charges were linked together by lines of force in empty space. However, even though his idea was easy to see in the mind's eye, it introduced an intriguing scientific question. Would a vibrating charge set the lines of force into vibration? At this point, Faraday might have pictured each line behaving as if it were a linked row of mechanical oscillators. And in that case, he would have seen a disturbance propagate along the row, either as a longitudinal wave or as a transverse wave. But no matter how they might have taken shape in his mind, the significance of those vibrations was in the fact that Faraday had seen them. And somewhere between the lines of Michael Faraday's Thoughts on Ray Vibrations, James Clerk Maxwell would discover his electromagnetic theory of light. However, before he could read Faraday's handwriting on the wall, to refine and polish it with his elegant mathematics, Maxwell needed to decipher a crucial clue. Within the forces of electricity and magnetism, he found a very significant speed. Any wave has a definite speed, depending on what makes it go. For example, in deep water, the speed of waves depends on the acceleration of gravity and the length of the wave. In air, the speed of sound depends on the air pressure as well as the density of the medium. And for linked oscillators, the speed is given by the spring constant, the mass, and the distance between oscillators. So it was time for Maxwell to get down to determining the speed of waves in Faraday's lines of force. From Maxwell's mathematical perspective, Faraday's lines were an expression of the 1/r² nature of the forces of gravity, of electricity, and of magnetism. At the same time, each of those has a specific constant. And in the right scientific hands, those facts got around to this. Since the fundamental forces of electricity and magnetism aren't independent, the electric constant, K sub E, and the magnetic constant, K sub M, should be related. But the question is, how? The ratio, K sub E divided by K sub M, has the units meters squared over seconds squared. In other words, the square of a speed. But what speed? Its square is 9 times 10 to the 16th meters squared per second squared. Divide the electric constant by the magnetic constant. And there it is, the speed of light.
Take your electrification by separating.
It was an amazing discovery.
Now we can have a spot of tea.
After 50 years of the closest scientific scrutiny elsewhere, James Clerk Maxwell saw the light and found its speed in the forces of electricity and magnetism.